Good afternoon. Please, every time we start from a question, so please tell me what you think. I don't know about you. I've learned something from my last lecture. Turns out I don't like looking into a huge room, seeing a few students. Or maybe I should practice more. Another snore day comes. Well, I am collecting your answers, and for the majority of the students, that should not be a new slide. You should recognize it from the past. And maybe you should recognize the feeling you had. Maybe not, I'm not sure. Bless you. So, yes or no question. Again, I don't know about you. I watch my lectures afterwards. Don't like what I see. Not like the way I talk, the way I walk, but that doesn't matter. What matters is two things: logic and clarity. And from my personal perspective, the last lecture so far was the worst lecture of this course. Well, what did you say? Because?
Why else would you ask?
Can't hear you.
Why else would you ask?
To trick you? I should have tricked you. I will, I promise. What is 15 times 3? What did I write? Why? No, I have no idea why. That's the first mistake I've made, and there's one more. I want to point at it because, well, it's a interesting moment. It tells something about how our brain works. If you watched the lecture, you would have noticed that despite the fact that this slide clearly says motion is constant acceleration, I actually said out loud twice, like right now. What did I say? Yeah, what do you read? So, what does it tell us? What do you think? Many, many interesting things. First of all, especially for pre-med students, our mind plays tricks on us. There is industry built on that, magicians, illusionists. Plus, there is a rule, trust but verify. Usually we apply that rule to other people, but you should also sometimes apply that rule to yourself, because we might trick ourselves into thinking something which is not right. But more importantly, for this particular situation, you should follow the logic, and if you see something strange, like 15 times 3 is 75, what do you do? You act. Lecture 1, slide number 13. You should be active, and this is one of the action. You should ask a question or send an email with the question just to make sure that every step of every solution is absolutely correct and clear. Otherwise, any misconception might stay forever and, well, eventually lead to other misconceptions. This is like you're looking at your best friend and you say wrong name. There is no reason for that, just our brain works mysterious ways sometimes. Well, that's what we talk about right now. Continuing talking about relative velocities. This is the law. And basically, we just have to apply this law to different situations to see how it works. All right. You should read it, and simultaneously, while reading it, start drawing a picture using your imagination, the picture which represents this situation. And by now, you should feel some kind of familiarity, because when yesterday or today in the discussion, you had a similar case, the round trip. That's what we call the round trip. So please draw a picture. Training plane makes a round trip. First it flies 112 kilometers due east, and then it flies back. That's what round trip means. What's average displacement? As total, yeah, as average, total displacement is 0, average velocity is 0. So, and the pilot measures the speed of the cloud. Why does cloud move? What's the reason for that? Yeah. And the question is not what relative to what. The question is, what is the reason for this cloud being in motion? Wind. No matter if the pilot looking or persons from the Earth looking at it, because we read further, there's wind. Yeah, that's why is the physical reason for the cloud being moved. And of course, relative to the ground, it moves with one velocity, but relative to the plane, it moves with another velocity still moving. And now let's just draw the picture. Velocity of the plane relative to the ground. East to west. First it flies, no, you're absolutely right. Again, from the discussion, you should know it doesn't make a difference for the trip, but we have to be as accurate as possible. So, due east. And that's the velocity. Well, this is just a direction. I could call it an x-axis. And the velocity is a vector. And I want to keep subscripts which provide as much information as possible. So that's velocity of the plane relative to the ground on its way from west due east. And of course, there is velocity of the plane relative to the wind or cloud. Probably cloud is better, so we wouldn't have two W's. Velocity of the plane relative to the cloud on its way. And there is the velocity of the cloud, which is the velocity of the wind relative to the ground, the velocity of the cloud relative to the ground. Do we need any additional symbols? No, because plane flies back and forth, but wind blows in the same direction always. How does it point? A strong wind, okay, again, this arrow also points due east. Now, what do we know? This is 20 meters per second. Is related to which v? That's the person from the ground announced via radio. So that's relative to the ground, about the cloud or about the wind. So 20 meters per second, that's the magnitude, that's the speed of this velocity of the cloud relative to the ground. Now, this number, 300 meters per second, that's a critical moment of the whole solution. We only have two choices. We should assign this number either to the magnitude of this velocity or to the magnitude of that velocity. We do it right, the rest is kind of just straightforward, the reasoning. We do it wrong, well, everything goes wrong. So this is what I want to ask you right now. 300 meters per second, one. Is it the magnitude of this velocity of the plane relative to the ground on its way from west to east, or is it the magnitude of this velocity of the plane relative to the cloud? What do you think? It's starting happening. I'm getting lost clickers. So if anybody lost a clicker, maybe it's yours, I don't know. By the end of every semester, I find like a dozen clickers left behind. After 5 years of teaching, you can imagine. So of course we have to reread the problem, and what does it tell us? Pilot measuring velocity of the cloud. So the pilot measures the velocity of the cloud. 300 is the velocity of the cloud relative to the pilot. But what the question is about, the velocity of the pilot relative to the cloud or to the ground. So oops, come back. Sometimes they have powers. So the velocity of the cloud relative to the plane has the magnitude which is equal to 300 meters per second. Pilot measures this number, right? So that is a hint. Let's say you're a pilot, you're looking at the cloud, and you see the cloud flies towards you. Now imagine that there is a demon on the cloud looking at you. That demon will be measuring the velocity of the plane relative to the cloud. So there's velocity of the plane relative to the cloud, and there is the velocity of the cloud relative to the plane. What is the relationship between these two vectors? Anyone? Yes, in one word, opposite. They have exactly the same magnitude in opposite directions. That's it. So we just said this, they have exactly the same magnitude. So that should be PC or CP, doesn't matter. Very good. So I assume that means I'm not sure, which is a perfectly reasonable answer. So now we know what to do. So this velocity of the plane relative to the cloud points right now to the right, and the magnitude is 300. And what we're looking for now, the velocity of the plane relative to the ground. So the velocity of the come back. In moments like that, you really don't want to know what I think. So the velocity of the plane relative to the ground, I hope you have a copy, plus it's in the video, supposed to be equal to the velocity of the plane relative to the cloud plus the velocity of the cloud relative to the plane. So, which means this plus this, which means this. And the magnitude of this velocity of the plane relative to the ground when it travels from west due east, will be equal to the magnitude of the velocity of the plane relative to the cloud plus the magnitude of the velocity of the cloud relative to the ground, 320. Why do we need that number? Well, we are looking for how much time does it take to travel one way from west to east. That's the distance. Well, in meters. And to calculate time, let's say to the right, all we have to do is just this distance over speed. So 11200 over 320. Don't remember. I got 35. What do we get? Seconds. I know my handwriting, especially on the screen, is not really clear. So now, what do we do? Now, on its way back, this arrow is supposed to represent the velocity of the plane relative to ground, and a similar arrow is supposed to represent the velocity of the plane relative to cloud, and this arrow still represents the velocity of the cloud relative to the ground. So, what we need to do is to apply this law. They point in opposite directions. So, what I want to say is that the velocity of the plane relative to the ground is equal to the velocity of the plane relative to the cloud minus the velocity of the cloud relative to the ground, okay? So this is what I want to say. And now I want to ask a question. Yes, that's absolutely the right way to do it. No, that's absolutely the wrong way to do it. Any other button means, I don't know, I'm not sure. I don't care. This is not a tricky question. We just need to apply the law of relative velocities. And the law of relative velocities, what does it say? No, that's not what the law says. You cannot provide your interpretation of the law. You have to repeat the law word by word because that's the law. You know. So, anybody else? But it doesn't mean you're a bad person, right? It just means you may have forgotten certain parts of the law, and now when you need to answer it, your brain plays tricks on you.
Isn't it efficient?
Well, again, that's exactly what I'm asking. Please tell us the law. How does it sound?
Vectors,
Yeah,
velocity,
yeah.
equals velocity plus.
That's exactly right. V31 equals V32 plus V21. Actual nature of those objects don't matter. So if I want to write the velocity of the plane relative to the ground, I have to write the velocity of the plane relative to the cloud, and I have to write a plus velocity of the cloud relative to the ground. And it doesn't matter if the plane flies to the right, to the left, up, down, crashes, doesn't matter. That's the law. So if you said yes, that's a wrong answer. We must write a plus. Do not alternate the law, just in case. But, you see, if you want to tell me that if you want to calculate the speed, that would have been a completely different situation because speed is the magnitude of velocity. Velocity has components. They could have been positive or negative, but speed is always positive. So if we look at this picture now, yes? The velocity of the plane relative to the cloud plus the velocity of the cloud relative to the ground should give us a shorter arrow to the left. So to calculate the speed of that shorter arrow, plane relative to the ground, the speed magnitude, the magnitude of the velocity of the plane relative to the ground on its way east to west, supposed to be equal to the magnitude of the velocity of the plane relative to the cloud minus the magnitude of the velocity of the cloud relative to the ground. So the law of relative velocities is literally the law for velocities. First, we have to apply the law using velocities, treating velocities as vectors. Then we look at it, and then we extract information about speed, which is the magnitude of that arrow, the length of it. That's why the vector addition is very important. So now we're golden. So on its way back, the speed of the plane relative to the ground will be 20 meters less, but the distance traveled is the same. So this is time one way, this is time back. Total time is one plus another one. I guess I've missed a zero in my previous calculation, and no one said a word. Yeah, I missed a zero. 350. Yes?
Plane's going 300 meters per second and it's flying in the same direction.
Just a sec. So this is cloud, and this is the plane. This is the velocity of the plane relative to the cloud. But now, because the cloud is also moving relative to the ground, and this is the velocity of the cloud relative to the ground, the velocity of the plane relative to the ground will be, well, this plus this arrow, and its magnitude, of course, is this magnitude plus that magnitude. And now on its, which was which? Cloud. So now this is what's happening. This is the velocity of the plane relative to the cloud, wind. But wind still moves it slightly back. So now this arrow plus this arrow, and we are adding arrows, give in the result I made it, I can break it. An arrow which you see has the length which equal to this length minus this length. So we are adding velocities but subtracting speeds in this situation. We are adding velocities and adding speeds in this situation. We are always adding velocities. What do we do to speeds? Depends on the situation. Clearer? Okay. So this is the question we want to analyze now. Crossing the river. The difference between the previous problem and the new problem is that this is a two-dimensional motion. So that's why I want to mention something about two-dimensional motion. The position vector has two components now. And, well, this arrow represents the x component of the position vector. This arrow represents the y component of the position vector. And what we read here, that's what we call the x coordinate of an object. What we read here, that's what we call the y component, y coordinate of an object. Everything we've said before stays correct. Average velocity is still displacement over time. Displacement is a vector. So average velocity or instantaneous velocity or average acceleration or instantaneous acceleration might have two components now, x and y. So this is only one example of many examples we can write for two-dimensional motion. But if we know how to analyze one-dimensional motion, we know everything about two-dimensional motion. There's a hint I want to show you. So let's say this object travels in a very complicated manner. That's a trajectory. For the moment, we can forget about, well, y-axis, for example. We can imagine that the x-axis represents some kind of a screen, like this one. And here we have a set of very bright lights. So right below this ball or object, we're going to see a shadow of it. Shadow. And that shadow will be moving either right or left or right. So this shadow makes one-dimensional motion parallel to x-axis. And what do we know? What do we know about one-dimensional motion? Everything. So now we can imagine that y-axis represents a large screen, and we have a set of very bright lights to the right. So in that case, here on the screen, we'll be looking at the shadow of this object, and that shadow will move either up or down or up. So that shadow also makes one-dimensional motion. So basically, two-dimensional motion represents two one-dimensional motions combined. That's it. So now let's apply this reasoning for this problem. I'm not going to ask this question. Let's just analyze it through. You're trying to cross a river that has parallel banks, and you should aim your boat in such a way so you want to cross it as fast as possible. Shortest time. That's the goal. So, picture the river. Let's say it flows down or north-south, or you can call it any direction. This arrow represents the velocity of river, water, relative to shore, ground. What does it mean? It's always kind of helpful to imagine an actual situation related to this. It means that, for example, if there is a person looking at, I don't know, small piece of wood, a leaf, on the surface of water, the velocity of that small piece of wood relative to that person will be this. That's what it means. Now, let's say we start here. In general, we have only three options to consider. We can aim our boat like this, downstream. We can aim our boat like this, perpendicularly to the stream, or we can aim our boat like that, upstream. Only one option gives us traveling across by the shortest time. Which one? Well, here, let's imagine that this x-axis is a screen, and we have a set of very bright lights. So what we're looking at is the motion of the shadow of that boat. So of course it moves to the right, and this arrow, this red arrow, represents the velocity of this shadow relative to the ground. Questions on this part? So we need to relate this, the velocity of the shadow, when I'm very close to the edge of the screen, of the shadow relative to the ground. We need to relate to some of the features of the velocity of the boat relative to water. So, well, let's take a look at each option individually. So that's what we call the option A, option B, option C. Option A. This is how I aim my boat. So this is the velocity of the boat relative to the river. To get the velocity of the boat relative to the ground, I need to add velocity of the river relative to the ground, like this. The velocity of the boat relative to the ground is equal to the velocity of the boat relative to river plus river ground. So this blue arrow should represent, in general, the velocity of the boat relative to the ground, case A. As any vector, it has two components. This component represents Vx, the x component of the velocity of the boat relative to the ground, and another component at this point doesn't matter. Next picture. Case B. That's case A, case B. All these arrows should have the same magnitude. It's the same velocity of the boat relative to the same water. We just aim it differently. So the same magnitude, but direction points like this. That's the velocity of the boat relative to river. This is the velocity of the river relative to the ground. So now this blue arrow represents velocity of the boat relative to the ground, case B. And of course, it has two components. This is the x component with the velocity of the boat relative to the ground in case B. Well, case C, same reasoning. The velocity of the boat relative to river, same magnitude, but direction now down the stream, plus velocity of the river relative to ground. We get this red arrow, velocity of the boat relative to the ground in case C. And again, it has two components. This blue arrow represents the x component of the velocity of the boat relative to the ground in case C. Now, keep in mind, we don't really care where will we land. Here, 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 here. All we care about is how fast we will touch another shore. So basically the question is, which of these cases gives us the fastest motion for the shadow? A, press 1, B, press 2, C, press 3. Anybody wants jewelry? I've got a lost and found box right here. If you've lost something in this room, you can browse and maybe you'll find something. Yours, maybe not yours, but nice. We have seen this experiment before. I just want to, again, very quickly repeat it. Actually, there is a person I want to call Mr. Chris Lombardo. Chris Lombardo? That's the last learning assistant I haven't met yet. And I know just recently I've learned they require it to be here. Okay. Check. So, anyone, could you please just be ready if this card falls off, just grab it, anyone. Can you do that? Okay, thanks. Just be ready. So again, this is how I aim my boat, let's say, perpendicularly to the stream. That's the velocity of the stream. What's going to be the velocity of this boat relative to the ground be if I do it? Okay, great, thank you. You want to see it again? I mean, you want to see it again on the screen, right? Okay. Remember your choice, and if you still haven't pressed anything, keep pressing. So that's the velocity of the stream relative to the ground. And let's say, again, I want to aim my boat at 90 degrees to the stream. So that's going to be my velocity of the boat relative to the water, to the stream. So again, if I have a raft which flows with the stream, the boat will be aiming at this raft all time. That's why I always have a backup. Oops. Don't worry, I got it. So, clearly, it was aiming at the raft all time, but the displacement relative to the ground clearly is a certain angle. Oh, thank you. But I have to tell you beforehand, anybody who helps me not going to get any extra points anyway. It just, yeah. So that's the velocity of the boat relative to the ground. Now let's see what you've answered for this particular question. So we should go back to, if you remember lecture 1, slide 5, there was a question from a student, is there any way to increase my grade, any extra credit? There is no such thing as extra credit, it doesn't exist. Just get your credit. All right, we have a nice distribution, and don't feel bad if you didn't answer correctly, because actually my picture is just not very accurate. I should have used a ruler, because it's important to see actual sizes for each component. So if I look at this component, compare with this component, and then compare with this component, from my point of view, this one is the longest one. So this component represents the velocity of the shadow relative to the ground. So if your boat travels like this, so this motion doesn't interfere with the horizontal motion. So this shadow travels with the velocity represented by this component of the actual velocity of the boat. So the velocity of the x shadow is equal to the x component of velocity of the boat. So the picture with the longest x component gives the fastest crossing. And now we know everything. now we just have to draw only one velocity of the boat relative to water in order to travel as fast as possible, to have the shortest time out of all options. We should aim our boat at 90 degrees to the stream. So this arrow represents the first arrow represents the velocity of the boat relative to river, stream, water. This arrow represents the velocity of the river, water, stream relative to ground, shore. And if we apply the law of relative velocities, the velocity of the boat relative to ground will be equal to the velocity of the, to move it closer, the velocity of the boat relative to ground will be equal to velocity of the boat relative to river plus velocity of river relative to ground. In vectors, that's going to be this plus this. A tail to a head rule that gives us this. This red arrow now represents the velocity of the boat relative to the ground. So the actual motion from here will go like this, parallel to the velocity of the boat relative to the ground, and the shore will be reached here. This is how much stream does move it down the stream. Any questions? Because the rest is simple. If we want to actually calculate something, we need to know specific values. Like in this problem, we know that the river is 1,800 meters wide. We know that velocity of the boat in the lake is 4. The velocity of the boat in the lake, which is out of these 3 arrows, should represent the velocity of the boat in the lake. Yes, the velocity of the boat in the lake is the same as boat relative to water. River is water. So this is a 4. And the velocity of the stream, water relative to shore, 2. So basically, we have to draw a triangle one more time. We are crossing this river. This is the velocity of the boat relative to water, river. This is the velocity of the river, water relative to ground. That's the velocity of the boat relative to ground. The magnitude of this equals 4. The magnitude of this equals 2. That's it. If we want to, we can apply the Pythagorean theorem and we can calculate the magnitude of this. If I want to know how long does trip take, bless you, we have to use what number? 4, 2, or 4 squared, 16, square root of 20, 4 point something, 4.24. Yes? When I read this problem, I don't see any indication on the actual direction, so I choose the direction for everything. I choose to travel from east to west, and I choose to point the river, the stream, down from north to south. Okay, that's the first thing. That's my choice. And now, please repeat the question. Because I aim my boat straight at 90 degrees to the river. That's how I aim it. You know, if you drive a boat, you can manipulate with direction you want to travel to. That's what you call aiming. And the water still brings you down with itself. So if there is a person looking at your motion, that person sees you moving along this line. That's what that person actually sees from the ground. So this red arrow represents your motion relative to the ground. All right. So now, again, if we want to find out how much time does it take to cross, which number should we use? 4, 2, or 4 point something? Four. Okay. Thank you very much. I just want to write it down. It's going to be 1,800 over 4. That's how much time it takes to travel. Thank you. So by now you've solved two different problems. In the discussion you've solved the problem about shortest distance, and now we've solved the problem about shortest time. Two different problems. I will post the answer to discussions online.
I forgot to find the assignment.
I didn't bring it up.
Oh,
All right. 100% attendance. I didn't bring the sign sheet today, I forgot.
I have a question. On the side where you were doing the three options, you should go upstream, downstream, across. Why did you say one way across has to be that's quite helpful.
The fastest way would still be if there was no reverse pushing. It would still be this way, but then because of reverse pushing,
I have this for you. I also have a
your
question.
boat will go like even if it's pointing this way, your boat will
Where
like
you said 1800 over
slow
4.
down because of the reverse.
So isn't the
But then we still want to go
I don't
across
think so my number is 4.24 since the boat since the river is
this way
pushing
is
the boat
not
along. It's
resistant.
20 you have to use the total 20.
I'm going to ask you to run up.
You can collect this and I'll take care of
Professor, there was no attendance sheet today, right?
No, there is no. There is no. There isn't attendance sheet today. 100% attendance assumed. And actually, this is it. And you can take care of this too. All right, so here. If you're traveling from here, and you're trying, let's say you're trying to roll that way, and the stream brings you down, right? So your actual motion
Okay.
is like this.
Yeah.
And you land here, right?
Yes.
But it doesn't matter how far does the stream move you down. All we need to know is how much time does it take
To do the 18. Okay.
to cross 1,800 meters. 1,800 meters is this distance.
Yeah. So then that's assuming that there isn't like a current?
No. It means that the current doesn't matter.
Okay.
As long as we aim it like this, even if there is no current at all, still this arrow doesn't affect your motion
Okay.
from,
Yeah.
parallel to this axis.
So if there was a downward current, you would have to calculate the distance from here to here and then use that to calculate the time?
No, the time wouldn't be affected by your current at all.
Even though the distance is further? Because this is longer than this.
Well, this speed, of course, well, like 4.3, I'm not sure. Yeah, this speed, if you want to calculate time to travel using this speed, you need to know this distance.
Yeah.
So if you knew this distance divided by this speed would
Okay.
give you time.
Okay. Yeah.
But if you know this distance divided by this speed gives you the same time.
Okay. So the
It's the
question
same
was just
motion.
asked. Okay.
Yeah.
Okay. All right. Sounds good. Thank you.
Okay.
Hi, was there an attendance sheet on Monday? Because we didn't get it if there was.
On Monday,
Yeah.
it was.
We didn't get it passed back to us. We're in like the back row there. But if you do attendance through clickers? Because I clicked and stuff.
I do both, and sometimes still.
The phone's on the floor. It's on the way.
Sometimes clicker don't work. In that case, if you missed your sign-in sheet, you should send an email.
Okay.
Okay.
So
Just in case. Yeah, you said you should send an email and you should say that just in case you didn't sign in, but you're present.
Okay. Thank you.
Great. Awesome. Have a good weekend.
Professor, I have to give this to you. I'll be missing on Friday. I don't know if that matters, but I have to give to you. Cover letter.
Is it exam day?
I'm not sure though.
I'm only concerned if that's an exam day.
Okay.
If that's not an exam day, you don't have any seat problems, 1-2 days,
Alright.
that's not going to affect anything.
Okay, yeah,
But if it's an exam day,
it'll be a problem.
well, I have to accommodate you anyway, right? So, well, okay. So I'm going to hold on that.
Okay.
I'll see if it's interfere.
I'll go check.
Yeah, and if it doesn't interfere with exams,
It doesn't really matter.
yeah.
Okay. Thank you.
Get some more stuff. Take care of all this, and you can bring this up to the office. Someone left it was on the floor.
Okay.
People forget things.
Yeah.
Yeah. You can just grab all that stuff, and this is mine. I'm gonna take. You can actually put it together. I don't know. It's up to you. Wherever.
You want me to take this apart?
No. I'm gonna use it from now on.
Okay.